Good afternoon to everyone. In last class, we discussed about solid modeling techniques. They are constructive solid geometry, boundary representation. Today in this class, we will discuss about curve representations of non-parametric and parametric form. And next, curve representation of like analytical and synthetic surfaces. Next, surface modeling. Okay. First of all, representation of curves. Representation of curves, types of curves equations will be in non-parametric. They are classified into two types. One is second one is the implicit form. Coming to parametric, equation will be x equal to x of t, y equal to y of t, and z equal to z of t. And what is the difference between implicit and explicit, and major difference between non-parametric and parametric curve representation? When coming to the difference between parametric and non-parametric means, in parametric curve representation, assume it underlies on statistical distribution. Okay, it calculates under statistical distributions. When coming to non-parametric, there is no chance to calculate any distributions here, only forming explicit and implicit curve representation. That is the difference between parametric to non-parametric. In parametric, we are doing statistical distributions for calculations. In non-parametric curve representation, we does not or we don't calculate any type of statistical distributions in non-parametric equations. Next, first one is representation of curves and difference between parametric to non-parametric. Okay. Coming to explicit and implicit. In explicit, these are all two classifications belonging to non-parametric equations. When coming to explicit equation, the representation will be y equal to f of x. Okay, that is related to non-parametric equation, y equal to f of x and z equal to z of x. When in implicit form, that is also one type of classification in non-parametric equation, but here we are combining all coordinate points. That means x, y, z, three directions, f of x, y, z, those three directions will be zeros. That is the difference between explicit to implicit curve representations. Next, analytical curves versus synthetic curves. In previous class, we discussed what are the different types of analytical curves and synthetic curves. Previously, I was told to you, in analytical curves, we have discussed about like points, lines, arcs, circles, fillets, chamfers. That means in analytical curves, more number of like planar curves, lofted surfaces, planar, lofted, tabulated, etc. But in these analytical curves, also discussed about chamfers, conics, like conic sections of ellipses, parabolas, and hyperbolas. When comes to synthetic curves, we are discussing about cubic splines, B-splines, Bezier curves, and beta splines. These are very important in CAD/CAM sections. Synthetic curves. Synthetic curves are Hermite cubic spline, B-spline, Bezier curve, and beta spline. Okay, next. For example, in this figure, I'm drawing a one circle with radius of capital R and showing three coordinate points with directions of x, y, z directions. The angle will be theta. It will be written in non-parametric and parametric equation. Written in parametric and non-parametric equation. When it comes to implicit, that means implicit or explicit. It is related to non-parametric equation. That will be x square plus y square plus z square, including radius minus capital R square equal to 0. That means the radius and the radius for all three directions will be 0, and z direction is also 0. When it comes to parametric equation, the top side implicit will be related to non-parametric. When it comes to parametric, we are doing statistical distributions here. X of theta, y of theta, z of theta. That means direction for all three coordinate points. Here I am taking coordinate points here and angle will be theta. First of all, I am calculating parametric and representing equation x of theta that equal to r of cos theta. Why I am writing r of cos theta? Because x will be in adjacent side. In trigonometric, we are doing and writing cos theta when it will be in adjacent side. Okay, x of theta equal to r cos theta. Y of same procedure as like x of theta. When y of theta is equal to r of sin theta, similar to x of theta. Here y will be in opposite direction. So I am writing r of sin theta. In z direction, z of theta equal to 0. Why? Because in implicit form, I am writing z equal to 0. So for that case, in parametric also, z of theta equal to 0. Next. Basic concepts. That means order of continuity. The order of continuity is a term usually used to measure the degree of continuous derivatives. Okay. Basic concept. In this, we are discussing about order of continuity, that it is related to zero order, first order, second order. First of all, we are discussing the definition for order of continuity. The order of continuity is a term usually used to measure the degree of continuous derivatives. That means C0, C1, C2. Under the definition, I am showing the difference between the order of continuity for zero order, first order, second order parametric continuities. First of all, what is zero order parametric continuity? That means first figure shows what is the difference between first order and second order over zero order parametric continuities. First figure shows about details of zero order parametric continuity. Definition of zero order parametric continuity is here in first figure I am showing two curves here. The two curves must have same coordinate position at the boundary point. That means C0 is the boundary point. Two curves joining at one point. That will be zero order parametric continuity. Okay. When it comes to first order parametric continuity, what is the difference between zero order to first order parametric continuity? That means in zero order we are following two curves. That means those are similar or unsimilar sections. But it comes to first order parametric continuity, those are tangent lines of the coordinate functions for two successive curves. Sections are equals. That means two tangent lines are meeting at one point. Those are successive curves meeting at one point. That is the joining point. Joining point will be C1. Next, second order parametric continuity. What is the difference between first order parametric continuity to second order parametric continuity? In the second order parametric continuity, both the first and second order parametric derivatives of the two curve sections. In this third figure, I am showing the details for second order parametric continuity. In this, both the first and second order parametric derivatives of two curve sections are the same at intersection point. That one is C2. Okay. Next. When Hermite curve, okay, up to now we are discussing about order of continuity and basic concepts of curve representation. From this slide we are discussing about Hermite curve. Okay, these are all related to synthetic curves. Up to now we are discussed about analytical curves. Analytical means points, lines, circles, chamfers, etc. and planar ruled surfaces, tabulated cylinders, etc. From this slide we are discussing about synthetic curves. Synthetic means Hermite cubic spline, B-spline, Bezier curve. First of all, definition for Hermite curve. Hermite curves are designed by using two control points and one tangent segment at each control point. In this below figure, I am showing what is Hermite curve and what are the two control points. Here in this figure, I am showing two control points. One is at first initial point u equal to 0 at control point P0, and second one is the P1 u equal to 1 at control point P1, and one tangent line starts from P0, that will be P0 dash. That one is the tangent line. Overall, four coordinate, that means four control points are here. One is P0 and second one is P0 dash. Third one is P1. Fourth one is P1 dash. Two control points u equal to 0 and u equal to 1. For 4 control points, 3 into 4. Why I am writing 3 into 4 here? Because of, first of all, initially 3 control points are there. After adding 1 tangential point, it will be 4. Okay, for that reason I am multiplying 3 with 4. 3 into 4 equal to 12 coefficients to be determined. That means 12 coefficients are to be determined by using Hermite curve representation. For representing Hermite curve, I am taking representation P of u. P of u equal to x of u, y of u, z of u transpose. That means I am taking 3-dimensional coordinate system here.